So hi everyone, this is the Deep Learning Bootcamp. We're going to start with homework 1, part 1. We'll spend a little time on that, but we'll spend far more time on homework 1, part 2. But first things first, I just want to say, read the write-up. Absolutely read it. Like, I know we get so many of these write-ups that are so long and stupid. It's okay to say that. Like, some of them, you read them and you're like, I am dumber for having read that. I don't know what that meant. This one is designed so that you can follow it and actually see the shapes, see the formulas, and straight up code it in. We're not trying to trick you, and all of the to-dos in the homework, when it says, you know, Z0, none, to do, it's only one line. It's not expecting like some incredible for loop that's going to go out into eternity. I don't want a list comprehension that is like amazing, that you found a way to compress it into one line. All of these can be done in one line when it says to do. All of those just expected to be one line. If you're taking more than one line, you're probably overthinking it. And that is going to be your biggest enemy, I think, for homework 1, part 1. In order to combat that, what I did is these examples can be worked out by hand on a calculator. I am old, very old, danger close to 40, and didn't get to go to school for computers. So I wanted to know that these things, this math actually worked on a calculator, and it does. And so that is why these are written the way they are, so that you can check these examples by calculator. So if your code doesn't line up with you punching in the numbers in a calculator, you're probably wrong. That being said, I'm not infallible. So if the code is wrong or the example's wrong, let me know, because I'd like to fix it for future generations. You guys get to be the test dummies. You're literally the first ones to see this. What we'll do today, just to kind of show you that I'm not trying to be the boogeyman, we're not trying to do anything scary. We'll go through MLP 0 from homework. So what this is a very, very like super simple neural network of just kind of 0 layers. What we're going to do is code this together, and to show that I'm not tricking you or anything like that, just pulling up the fresh thing, and hopefully you all will work with me, and this won't just be me talking into the camera. So at this point in the homework, by the time you get to MLP 0, you have already built your linear layers, you've done your activations, so you can call them. And you won't need to reinvent the wheel by the time you get to these. And so I'm going to show you here how simple that is when it comes to putting it in place for an actual neural network, be it a very simple one. And you see, we give you all these, the layer, it's a simple 2 to 3, as shown here in the diagram. It has the 1 activation layer, which is the ReLU. This is all given to you in the code, and this is what that would look like drawn out. But you're not going to have to worry about all these things, because you've already coded them in at this point, and you did that in the simple linear and the ReLU parts of the homework. So I'm going to put somebody on the spot unless someone wants to help me. So from here, what do you have to tell? So you're given A0. What do you have to do to get Z0? Is anybody able to chime up and help me?
Multiply by weights and add the bias.
That is what you do in linear. You're right. But since you've already done linear and you've created that layer and we're giving you a list of that linear layer, literally all you have to do is call that layer and tell it to go forward. So you're saying self.layers, which we've given you right there. We're saying, all right, that one layer, I want you to go forward. And it's no trick here. You've only been given one argument. So what do you feed it? There you go. And that's Z0. You're cheating on the test. That's the exact answer for homework. So anybody who showed up today gets that for free. But
some transpose stuff as well, like np dot a0 comma transpose, and then, or is there something else?
So that's when you start, you're thinking inside linear. So if we were doing this and I asked you how to build forward, then you would start doing those things. So what you're saying is, how do I build Z in linear? And we could do that as well, but I mean, that it's going to be straight from the write-up. And I mean, that's a good practice for you to just write the code that is the formula is given there. It's you know, W times B transposed. So it's not a trick. You know, there it'd be here and here for A to there. So when you do linear, that's how you'll figure that out. So you see, they give you W, they give you B, and you'll just copy the formula. Like, don't make it hard, and then you're going to see that the return for that is going to be Z, and that's why here we're able to just go, okay, Z0 is A0 going forward, and then A1 is going to be the exact same thing, is just a different layer going forward, which A1 is going to have the activation layer F0 go forward in this point. To Z0 activation layer goes forward to make A1. Does that make sense? So
Yeah.
So if you would want to add a new layer, would you have to, like, in the layers list, would you have to add linear 2, 3 again, or something like that, or 3, 2?
yes. So if we went on and did MLP1 and you're given more layers, you would do the similar thing for each of those layers. Does that make sense there? As here you've gone not only from Z0 to A1, you'll then go from A1 to Z1 to A2. And so looking at that in a diagram might help you the most. So this would be a diagram of MLP0, this would be MLP1.
Are these diagrams available?
If they're not in the write-up, I will put them in Piazza. These are something that we had used to create all this. I do believe they were definitely in a draft of the write-up, so they may be in the write-up, or just cut into sections.
Okay.
So if not, come see me in office hours, and I will most certainly use these to teach you all. So I think the bottom line here is, don't overthink it. It's going to be the same process with backwards. You know, you're gonna go through this just as simply because you've already created those layers according to the write-up. And I mean, I cannot tell you enough. Just use the write-up, and it will save your life. And there you go. So there's your first thing. Somebody's making a lot of noise. If we could. Thank you. All right. If there are any direct questions you all want to go over on that, we can touch base on them. Go ahead.
Yeah, a quick question about the differentiation for the backpropagation. How are we expected to implement the differentiation?
When you do like linear backwards, yes, you'll do all these and use the write-up.
Okay.
Go ahead, Ronadi.
Hi, I had a question about your line 18 in the homework one. I think you did A1 equal to self.f forward A1 again in homework one file, line 18. I think, do you mean Z1, forward of Z1?
Oh yeah,
Sorry,
it's actually Z0. Z0. Thank you.
Yeah.
Was trying to talk and type at the same time. That did not work. But good catch. I'm glad people are actually paying attention. You know, pay attention to the screen, not my hands, kind of thing. All right. And Srinivasan.
Yeah, just one small question about backward for MLP. So in the auto grader, it said they're also looking for DW0, but it's not really provided. So I was like confused because for the previous parts, you didn't have to like add in things that weren't there. But it seems that for this one, you have to like add in two variables and calculate the formulas.
So for DW0, as you're going backwards, I think what they're going for is wanting you to have some intuition as to what all the derivative of any of those things means. So you should understand that what that is how much it is impacting whatever it is the derivative of, like for instance, you know, DLDA, you know, how much that DA is impacting the loss, you know, if they're not expressly written out, just think about the relationships, and I think you'll be able to get them. If not, come see us in office hours, Piazza. I have office hours directly after this, so I'm happy to answer questions because I know a lot of people were worried about homework 1 part 2. So I'm going to pass it on to Wen, and like I said, I'll go straight from this to office hours and field any more questions. Wen, on to you, buddy.
I have. So can I ask another question about the backward?
Can I ask?
Sure.
In Bradley's code.
Go ahead.
Yeah, I just want to know like how the backward is calculated in this one, in the like across the layers. So I know for the backward for the output layer, you just need to call the backward function, but to calculate the intermediate gradient losses, how should I do
Okay,
that?
so for instance, DLDZ0, is that something everyone wants to address real quick?
Yes.
Yeah,
Okay.
sure.
So going back to exactly what we were talking about. So DLDZ0, you want to know the loss, which is here. What is impacting what is having an impact on the loss between here and here is the way I look at it. And so with that, what you're going to see, I mean, without even having I mean, this is some chain rule stuff, but which I'm by no means am I a calculus professor, but what it'll end up being is, and I hope this makes sense with the diagram I just provided, is DLDA1 times does that make sense? These are the things that are impacting each other in relationship to the loss. I mean, this is is that making sense to whoever it was who asked the question?
Yeah, it makes sense. But is the order correct? So now it's DLDA1 times DA1 DZ0.
Yes. And so then from there, because you've already built the layers, you'll then again be able to just go and that is all of MLP0.
Yeah,
So-
thanks. Line 31 is what I was looking for because I didn't know how to handle that line.
Okay. Oh, yes. So you'll implement that backward when you create linear here. And so the return for that is going to be something you want to keep in mind for how that impacts this. That makes sense.
Hi,
All right.
Bradley. I had a small request. Could you
Sure.
just resize your ID's window so that the diagram behind is also visible as you type? It's a little easier to relate.
All right. Well, I was just about to hand it to Wen.
Okay.
I have no idea what I'm doing now. But I will get these diagrams out on onto Piazza. I know the issue is going to be they don't use the exact same name conventions as the homework, and so I don't want to confuse people on the homework, if that makes sense. So I think it's a good picture of a neural network, but I don't want everyone to be absolutely married to this and go, oh, where did ones come from, and all that stuff. So all right, now on to you, Wen.
Thank you, Bradley. I will continue to talk about homework 1 P2. Okay. Homework 1 P2 will conduct in Kaggle, and if you haven't joined the computation, please join it. And here's the red tab. Please read it carefully. It contains many useful information. And about this bootcamp, I will mainly focus on the starter notebook. This one. This starter notebook is sufficient for your early submission. I believe early submission only require you to achieve 42 accuracy. As you can see the log. This notebook can achieve like 48 accuracy, so it's sufficient for your early deadline. Okay, let's start to go through this entire notebook. I will.
Hi, could you repeat the point about early deadline again? What is sufficient?
Okay. You can you see my screen? This one.
Yes.
Okay. Okay. So there are two deadlines. This one, February 17th, this one is the final deadline. And before the final deadline, there's an early deadline. So you need to achieve accuracy more than 42 to get your early deadline score, which is, I believe, is 7 points. And you need also, there's a little quiz about this homework 1 P2, and you need also answer that quiz on your canvas to acquire like 3 points. More details on Piazza. You can see the Piazza. Yeah, those are what you should do before early deadline, and those are about what you should do before the final deadline. You can check this post. Okay. I will continue to talk about the code. First, I will queue my instance. So the first step to use Colab to train your model is load your dataset to Colab server. And there are two ways to do it. The first one is you upload it to your Google Drive first, and you mount your Google Drive, use these 2 lines of code, and you copy this zip file to this Colab server and unzip it. I'll give an example. I've already uploaded my this dataset to my Google Drive, and let's execute it. Okay, it will. Sorry, it's not English. It's just acquire authorization to access my Google Drive. As you can see, once we finish this line, you have a G Drive folder here, and you can access all your files in your Google Drive under this folder. And so you can copy your dataset to the current catalog and unzip it. This is one way to load your dataset. And here's another way. You can directly download your dataset from Kaggle. But before do that, you need set your secret key. Those are the steps. Firstly, you type install the Kaggle package. Then you create a folder here, and you need to save your secret key in this file, kaggle.json. and this file should under this folder. And Kaggle will go there to check your secret key to identify you, and then you can use Kaggle API. This one, computation download, to download your dataset. Can we stop this one? No. Okay. Somebody may ask, where can I find my token? You can find your token under. Okay, let's go there. Under this account tab, under this API section, there is a button, create new API token. Once you click it, you will download a JSON file, which will contain your token. You can just copy the content to here. Please don't use my token. we will execute this to after this one, after the previous, once the previous one finished.
Do you have to load your dataset again every time that you start the notebook?
Yeah. You need to do this every time.
Only if you do it that way, but yeah, this is the easy way, but you will need to load it every time. If you do.
And if you put it on your Google Drive, you don't have to load it every time.
Correct, but it will take a long time and it makes it run real slow.
Okay. Why is it slower?
Okay, if you upload this zip file to a Google Drive, you need to copy it to your current service catalog. Otherwise, it's very slow. You can't just directly access file in your Google Drive because I don't know the actual network protocol are they using, but it's very slow. You need to copy it to your current catalog.
Does that not save once you do it once?
Pardon me?
So once you unzip or once you copy it to your drive, does that not save? Like once you turn off the notebook, do you have to re-clone or recopy?
Yeah. All the folders here, it will disappear once this instance stopped. So you need to do this every time. Every time you start a new collab instance.
So it would be better to put it on a drive.
I think I recommend this way. Use directly download from your Kaggle because you can see the speed is quite fast, just several seconds, and you unzip it. The total time is maybe 2 minutes, so I think it's okay.
Okay.
Yeah.
And do you know
Okay,
why
thank
it's
you.
slower if it uses the Google Drive?
This code, this line of code just mount your Google Drive under this folder, but the content, the files are not in this server, is in another distributed.
Then
server.
why do you mount it?
Why do I? Okay, here are two ways to load your dataset. This one is use you upload your zip file to your Google Drive and copy it to this current catalog. You can use this way, and there's another way. You don't use your Google Drive. You just set your secret token, and you download your dataset from Kaggle.
Okay.
Yeah. Okay.
It definitely works both ways, but you will find when the data sets get huge that it is significantly slower when you mount it on your Google Drive.
Okay, thanks.
Okay, let's go through the actual code. Here are some packages we need to import. Here are the benefits if you use Colab. Those packages are pre-installed, so you can directly import it Okay, this is a simple network we give you. Is the structure is quite simple, only 3 layers. One linear layer, one ReLU, another linear layer. And let's take a look. Firstly, this class is inherit from n.module. And basically all the neural network class should inherit from this n.module. And you should build your layers under this init function. And you should implement how to use these layers in your forward function. As you can see here, the 13 and here the 40. 40 indicate the number of classes. We have 40 phoniums. So the final dimension, the final output dimension should be 40. And this 13 is because each frame is a 13 dimension vector. We will cover it later. Each frame is a 13 dimension vector. So if you don't use context, the input should. Do you have a question?
Yes, there's self.lasers instead of layers. I don't know if that's a mistake or if it's on purpose. Self.lasers equals nn.sequentials. You see it?
Here?
No, the layers before that, like in the same line, but then self.lay, yeah, and there as well. If
It's a typo. Sorry for that.
And underneath as well, like definition forward, and then yeah. Right. Thank you.
Okay, thank you. It's a typo. If you
He was
don't use
consistent.
any
It actually would have worked because he did the same typo in both places.
yeah. If you don't use any context, the input size should be 13, and we will talk about this later. And the next step is let's talk about the dataset. We have 2 dataset class, library samples and library items. Library samples, basically it will read the NPY file, and each NPY file represents an utterance, and it will combine many utterance into one huge utterance. In that case, you can use your memory more efficiency. Let's take a look of this class. In the init function, we need to pass data path, sample, shuffle, partition, and the CSV path. This data path is the variable is a string to this path, to your data set. And the sample represents how many NumPy files will be preloaded for each get item call. In other words, it means how many utterance will combine together into one huge utterance. We will cover it in here in this function. And the shuffle is quite obvious. Partition. Partition means what kind of data set are you using? You can pass this one directly. If you pass this one, we will use data set under this folder. This is validation data set for us to validate the performance of our neural network. And you can also pass this one, train clean 100. This is our actual training data set.
Yeah, I have a question about that real quick. What does the MFCC stand for?
I'm sorry, I don't understand what this stand for. Maybe you can post a Piazza. I don't create this data set.
Okay.
But under this folder, those are the input. And under this folder, under the transcript folder, those are the labels.
All right. Okay.
this is how you use it.
So MFCC is a feature extraction technique. That's why it's named under that.
All right. Okay.
Okay, thank you. CSV, okay, the last one, CSV,
I had a question.
yeah.
So there are two directories by the name of test clean and as well as train clean 100. What is the difference between those two directories?
Do you mean those two folders?
Yeah, so there is one test clean that is here, and there is one test clean that is under the student data directory.
Oh, you can just ignore it because I
Okay.
I run two ways to load the data set.
Okay, all right.
Yeah, yeah. Okay, let's talk about this CSV path. This variable is the path to the CSV file we provide. I believe it's here, yeah. This CSV file. It contains a subset of training dataset for you to explore hyperparameters. If you are exploring hyperparameters, you can use this subset of training dataset because I believe the whole training set is the size of the whole training set is quite large. You need a lot of time to go through the entire dataset. If you are just exploring hyperparameter, if you just want to know which one is better, you don't need to go through the entire dataset. You can just use a subset of training dataset. Yeah, any questions?
So what do you adapt in order to use the subset?
You pass the CSV file like here. You pass this CSV file to this argument.
And nothing for the labels.
Yeah, we already processed it for you.
Oh, cool. Okay.
Yeah. Here we already processed not only the input but also the label. Okay. I believe I've finished the init function. Okay, here's 40 phonemes we have. Here's the 40 classes. This SLI indicates silence, and this SOS indicates start of sentence, and this one is end of sentence. And next we'll talk about this get item. Before talking about this function, you need to understand your data set. Here's the concept of phoneme. As letters are atomic elements of written language, phonemes are the atomic elements of speech. For this challenge, we only consider 40 phonemes. So those are these 40 phonemes. Yeah, questions? All the C. Are you asking question? Okay, maybe I will continue. So this is about our label. And how about the NumPy file under this MFCC? Each NumPy file under MFCC folder corresponding to an utterance. You can consider a piece of audio contains one or several sentences as an utterance. So each of these files contains represent an utterance. For an utterance t seconds long, it's a matrix of shape 100 times t and 13. This is the shape. It's a two-dimensional vector. And y is 13 because each frame a 13-dimensional vector represents a frame, and each frame represents 25 microseconds of audio. And we use this STFT, which is short time Fourier transform to convert it into a 13-dimensional vector. So the feature length is 13 and the y is 100. It's because we use a stride of 10 microseconds to slide over the utterance. And 1 second contains 100 of 10 microseconds. So the first dimension is 100 times t. And how about the label? The shape of label for that utterance should be a one-dimensional vector, and the length of that vector should be 100 times t. And since it's a classification problem, the data type is integer, and we only have 40 phonemes. So each integer ranges from 0 to 39. And I believe there's a graph in, okay, this is how we slide over an utterance. And here the typo is not 40, is 13. And here there is a figure. The first dimension is number of utterance, which is how many NumPy file we have. So this is a dimension, and for each utterance is a matrix, two-dimensional vector. This line indicates the length of the utterance, and this line indicates the feature length. And it's not 40, it's a typo, it's 13. So that is the data representation. Do you guys have any questions?
Can you explain how you like the third and the second dimension? Like I'm not getting it.
Okay. Each NumPy file is a little rectangular. Okay, so each NumPy file is a matrix, and each NumPy file represents an utterance. Utterance has length, so the second dimension is the length of that utterance, and the third dimension is the feature length. The feature length, as we mentioned here, feature length is a three-dimensional vector, and it represents 25 microseconds of audio. Did I answer your question?
Yes, thank you.
Okay. Jiachen, do you have a question?
Yeah, hi, Wenwen. So in one of the figure you said is the number is not 40, it should be 13. Can you point out which one was that?
Oh yeah, here is 13. Not
So
40.
this 13 means there are 13 elements in this frequency representation of the audio.
30 elements in frequency representation in this audio. Yeah, for each frame.
And a frame is just 25 milliseconds. So you take these 25 milliseconds and you run something like FFT to get these 13 bins.
Yeah.
Thank you.
Okay, I believe I finish this part, and let's keep going. So since we passed 10,000 to our sample, so this loop will execute 10,000 times. And for each loop, we append the one NumPy file into a variable. And at the end of this loop, we concatenate this huge NumPy file. So in the end, we combine like 10,000 utterances into one huge utterance here. This is the library samples. And next, we will talk about the library items. Let's use signature first. This X and
For concatenate, shouldn't there be two variables? Like I'm not getting how that function is happening.
Can you repeat your question again?
Yeah, in np.concatenate x, shouldn't there be like, there should be some two things to concatenate, right? Or more, two or more.
So are you confused about this line?
Yes.
Okay, maybe let's see what time we have. Okay, we still have time. Let's we can execute this. We can set a breakpoint here, and then to print it out to see what's really going on. Before that, we need to install this package. IPDB is a IPython debugger, and it's quite useful to debug your Python code in Colab. And let's execute it. Okay, we set a breakpoint here, and let's see what's this variables. Let's see this x path. So is a path to this NumPy file, and let's see what's in this y path. Okay, is a path to the label file, and let's see the label. So as we just mentioned, this label is a one-dimensional vector, and x data should be a matrix. Yeah, it's a two-dimensional vector, so it's a matrix. Let's see the shape of this x data and the label. So the shape of this one is 1513, and let's see the shape of that label. The shape of the label is a one-dimensional vector, and the length is 1500. And then let's see what's inside this x and y. So x is a list. It contains several matrices. Y is also a list. It contains several labels. And at the end of this loop, those matrix will be combined into a huge matrix. It will combine along the first dimension, along this dimension. So in the end, the first dimension of your x should be very, very long. And the second dimension is still 13. Yes, any questions? Okay, if there's no question, let's continue. So this x and y, x is a huge combined utterance, y is corresponding label. Here we only complete the situation when the context 0, and you need implement when the context not 0. I believe there is some hint in the right tab. Yeah, here. You can implement your code based on those hints. And about this get item, it will return one frame with or without context. In this case, it directly return one frame, which is a 13-dimensional vector, and directly return its label. You need to implement the situation when the context is not 0. Context is a very important hyperparameter in this homework. So you need definitely implement it and try different contexts to get a higher score. Okay, the next block is training stage and the test stage. I believe I've already covered the training stage in recitation 1. And if you're not familiar with it, please check that recording. I will quickly go through this main function. So in our main function, we create a device object. We create okay, here's one thing. When you are using Colab, please make sure you use GPU as your accelerator, hardware accelerator. Otherwise, you will train your model on CPU, which is very, very slow. Here we create a device object, and we create a model object, and we transform our model object to the device memory, and we use an Adam optimizer. You can try different optimizer. I believe there is a table. Yeah, there's a table. You can try different combination of those hyperparameters. For example, for optimizer, you can try vanilla SGD, Adam, or Nestrov momentum. You can try different optimizer to find the best one.
Are those suggestions, or do we have to stick with them?
I'm not sure if I can give you some hint about hyperparameter. If you have,
You don't have to stick with any of the hyperparameters we give you. Like really the only rule is you have to use an MLP.
Okay.
yeah.
And
Okay.
another small question: the torch this .device line, is it also necessary if you're working in Colab?
Yeah, it's necessary.
Okay.
Yeah, if you want to use a GPU, you have to do that.
All right.
Here we create a model object, and we create a Adam optimizer object, and here we use cross entropy loss as our criteria. And here you can see we create 2 library sample object. The first one is for training. As you can see, we pass this train clean 100 to this partition argument, and we pass this CSV to use only a subset of the whole training subset, the whole training data set. And for this object, we pass div clean. So this data set object is for validation. And as you can see, we pass this train sample to our training stage and pass this div sample to our test stage.
So you only use the CSV path parameter if you want to use a subset, and else you leave it blank.
Yes.
Okay.
Yeah, that's the end of this speech. And as you can see, for that simple network, we can achieve like 48 accuracy. Just this simple structure. And you need definitely try different architecture to get a higher accuracy. Yeah. So do you guys have any questions?
Yeah, like, can you explain, like, there is one more data set class, right? Libri items, like, how is it like working with the Libri samples? Can you explain it, please?
Which part?
There is another data set class, I guess.
Oh, this one?
Yeah. Like, how are we using this class? Like, I can see the working in this class, but how are we using it in the like?
Okay. So, so this class is library sample. This object is the object of library sample class, and this X and Y is this X is a huge combined utterance. And we pass this to a library item class to get an object. And we pass this object to data loader. In data loader, you need to indicate the batch size. Here, my batch size is 246. You can try different numbers. And once you get your data loader object, you can just iterate through this data loader object. So it's quite, so from here, just from this line, it's quite a standard data loader code here. So am I answering your question?
So each library item will be labeled with one phoneme.
Not one phoneme. This one is a huge utterance. For example, this one could be very long. For example, like the first dimension could be hundreds of thousands, and the second dimension should be 13. And the length of this y is equal to the first dimension of this x. So it contains many labels, not one label.
Okay.
Yeah.
So the train underscore samples I, that one like one value has multiple, you can say samples, right? X and Y. So like, won't that exhaust and give a error, kind of like out of index error?
Out of index error. No, because we implemented this length function here. If you implement this one correctly, as you can see, we iterate through the length of this object. So if you implement this function correctly, under this function, you will not get out of index error.
Okay,
Yeah.
thank you.
I have a quick question.
Yeah.
So the length of samples is equal to the number of NumPy files. Is that correct?
Equal to the number of, no, because we, if your sample is 1, in that case, it's equal to your number of NumPy file.
No. Can you go back to the part of the code you were discussing before this? Yeah, before this you were discussing
Before
samples, right?
sample class, this class? Which part?
Not this class. I think library items you were discussing.
This one?
Yeah.
Okay.
In training for this. Yeah, here we run the for loop for train samples, right? The length of train samples.
Yeah.
So this is what I was asking, is this length of train samples, will it be equal to all the number of utterances, which is like the NumPy files?
Okay, let's take an example. For example, if you use training samples and under this folder, I don't know exact number, but let's see, it's let's say 13,000 of NumPy file. And if you pass 1 to your sample, this length should be 30,000. But normally we don't do that, because in that case, your data loader will become very slow. you cannot efficiently use your memory. So like the default setting, we like pass maybe 1000. Let's take this as an example. In that case, this one, this one should be 30.
So is
Because-
one is 1000 the batch size then, or
pardon me?
sorry, yeah, is 1000 then the batch size, or where do you put in the 1000?
Like, where are you defining this 1000 here exactly?
1000 is you can consider the hyperparameter. How many utterances you want to combine together to use your memory more efficient.
So
You
is
can
the batch?
choose this number? Yeah.
So it is the batch size.
Not the batch size. Batch size is here. Okay, let's continue to do this. So if your sample is 1000 and in total you have 30,000 of NumPy file, you combine your utterance, you combine 1000 utterance into a huge one, which is this one. This X combined with 1000 utterance. And I don't know the exact number, but let's take an example. After you combine 1000 utterance, let's maybe let's say the shape of this X is this much. And here, if your batch size is like 32, so for this loop, it will execute this times, not 30, 32 times. Yeah, this times.
Okay, yeah, I see. Thank you.
Okay.
Thank you.
So any other questions? Okay, I believe it's already 2 p.m. ET. So if you have any other question, you can create a post on Piazza. And this will be the end of this bootcamp. Thank you, guys.
Thank you.
Thank you.